All right, to continue on with our discussion of operational amplifiers, specifically the ideal op amp, we're going to see that what we derived in the last video is actually going to allow us to do to develop a couple of different circuitries that are going to be very, very important to us, and kind of really, really cool functions that normally we're not really looking at within circuits 1 and circuits 2 material. And it's just kind of a step again into this like kind of bigger picture that I just think it's just so cool, man. So we're going to look at basically 4 different circuitries and basically how we actually develop the relationship of the output voltage to the input voltage. We're going to look at the non-inverting amplifier. We're going to look at the inverting amplifier. We're going to look at a summing amplifier and a difference amplifier. And utilizing those conditions that we had, that V1 and V2 had to be the same, and because of that, and also the fact that the internal resistance was so high, or basically approached to infinity, we saw examples where that internal resistance was 2 million, then we can't have any current through there. And so due to those notions, we actually can go ahead and apply nodal methods, KCL, very, very quickly, and actually determine that relationship between the output voltage and the input voltage very, very, very efficiently. So we're going to go, well, we could say like almost lightning speed through each of these, but it explains exactly how these relationships of the output voltage to the input are actually really derived. So let's take a look at the inverting amplifier first. And so that's when we actually have the source connected to the negative terminal. We're pulling basically positive down to ground. Now, due to the fact that basically positive is connected to 0 volts, that means that this node up here that's connected to to the negative terminal is actually also going to be 0 volts as well. No current going into that terminal, obviously. So I1 is equal to I2 flowing through the feedback resistance, and then I1 is flowing through that input resistance. And so here, Vx obviously, like we said, is equal to 0. So in this case, I1 is equal to I2. Rewrite the equation really quickly, Vs minus Vx over the input resistance, and that's equal to Vx minus Vout over the feedback resistance. And so Vs minus 0 over Ri, which is equal to 0 minus Vout over Rf. We find that if we look at the gain, remember Vout over Vs, then that's equal to minus Rf over Ri. Very, very, very simple. Or if we wanted to find Vout directly, we would just say minus Rf over Ri multiplied by Vs, that input voltage. So, but see, we get that negative on the output, so that means that we're looking at an inverting amplifier. But what if we don't want to invert that polarity on the output? Well, all we have to do is look at the non-inverting amplifier. And I'm going to move this over because I don't want to continually, I'm actually using 4 boards today. So we're going to look at basically the non-inverting amplifier and the summing amplifier together. So you guys are probably looking at the right side and going, oh my God. So the non-inverting amplifier, here we actually have the source connected to the positive terminal, and then basically at the negative terminal, we're going to connect that to the feedback resistance, and the input resistance, we're going to pull that down to ground right here. And so obviously here, in this case, Vx is actually just going to be equal to Vs. That's source voltage right there. So if we apply KCL again, I1 is equal to I2. Remember, current can't go into the op amp based off of that internal resistance and the fact that these two are actually equal to each other. So in this case, I1 again is equal to I2, but this time we're going from ground to Vx. So 0 minus Vx over Ri, and that's equal to Vx minus V0 over Rf. Here, Vx is just equal to Vs, so if we go ahead and substitute, we get minus Vs over Ri, and that's equal to Vs minus Vout over Rf. So in this case, if we go ahead, rearrange the equation, we get Vout over Rf, and that's equal to 1 over Ri plus 1 over Rf times Vs. We go ahead and simplify, so we get Rf times Ri plus RF over RF plus RI is equal to VS. In this case, RFs cancel each other out, and when we rearrange the equation a little bit, we find that the gain for a non-inverting amplifier is actually equal to 1 plus RF over RI. I have to do not erase up there again. I was actually intending to leave and go home and come back and do this tomorrow. Whoops. So in that case, we would actually say that V out is just equal to 1 plus RF over RI times VS if we want to know just that output voltage itself. All right. I feel like I'm moving quickly through this, but explain KCL is pretty simplistic, so I'm sure you guys are keeping up just fine. But obviously, if you have questions, message me. Summing amplifier. Here, we're pulling the positive terminal down to ground. And in this case, we're going to connect to Vx, which obviously Vx would be equal to 0. Okay? We're going to actually sum up V1, V2, and V3. So we're going to get 3 inputs. There are 3 different voltage sources, and we're going to connect those to Vx through R1, R2, and R3. Once again, we have a feedback resistance of RF up here. And so by KCL, I1 plus I2 plus I3 is equal to IX. So in this case, I1 is just equal to V1 minus Vx over R1 plus V2 minus Vx over R2 plus V3 minus Vx over R3. And that's just equal to Vx minus Vout divided by RF. But because we tied the positive terminal down to ground, Vx is just equal to 0. And then we get a very, very simplistic equation here. V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3. And that's equal to minus Vout over RF. And if we just go ahead and rewrite the equation in terms of Vout, Vout's just equal, and put the negative sign because it's going to do some inversion right there. And that's the polarity. That's just equal to RF times RF over R1 times V1 plus RF over R2 times V2 plus RF over R3 times V3. And whatever we find from the summation of those gets inverted in polarity right there. See guys, like once we went through and determined how the ideal operational amplifier works, we're able to quickly move through these derivations of the forms of each of these amplifiers very, very simplistically. But I really want to make sure you guys understood how we even got to this point. And right now we're able to just go through and develop these amazing amplifiers that are performing these functions for us. But obviously if we have a summing amplifier, what if we want something that would take the difference between 2 input voltages? Well, I got that for you next. Let's take a look. The difference amplifier is a little more complex in terms of deriving, but it's not complex, it's just more busy work essentially. So here I got V1 and V2, and I want to actually take the difference between V2 and V1. So here, if there's no current, see there's no current going into that positive terminal. Remember, we've already said that. No current there, no current there. 0 amps and 0 amps. But whatever this voltage has to be is right here, Vx, is going to be the same voltage at that node. So because there's no current flowing into the operational amplifier, the voltage at the positive terminal is just going to be a proportion of V2 based off voltage division. And so by voltage division, so here, Vx just exists across R4. And so Vx is just equal to R4 over R3 plus R4 and times V2. So this value right here that we would get actually exists here up here at Vx. So now we can write out our KCL equation and expand that and actually put this into such a form that we have just an entire equation based off the output voltage and related to the input, both of the inputs and the difference between the two. So in this case, here, I1 is equal to I2, And so V1 minus Vx over R1 is equal to Vx minus Vout divided by R2. And let me make a quick little correction right here. Yeah. And so if we go ahead and expand this equation out by substituting in what we had for Vx, then we get V1 over R1 minus 1 over R1 times R4 over R3 plus R4 times V2, and that's equal to 1 over R2 times R4 over R3 plus R4 times V2 minus Vout over R2. And so all I have to do is rearrange that equation now, and we can see right now that with whatever proportion that we get from this coefficient here times V2, we're actually going to subtract off R2 over R1 times V1. And so simply by rearranging this equation right here and relating it to Vout, we simply just come up with a different form that relates that output voltage to the difference between V2 and V1 based off of these proportions that we derived from KCL analysis of this circuit for the difference amplifier. And so in this case, R2 over R1 multiplied in the numerator here, 1 plus R1 over R2 divided by 1 plus R3 over R4. We multiply that by V2 voltage, subtract off R2 over R1 times V1, and that would actually give us the difference between those two voltages at the input. So I know that was pretty quick, guys, but the reason why we were able to go through and look at these amplifiers so fast was because of the fact that we were able to derive those ideal conditions. So what I want you guys to do with this video is go back and just look through these derivations. Look through this video probably a couple of times just to make sure you really understand, solidify basically the derivations of each of these amplifiers in your head. And once you do that, this stuff is going to start coming very, very, very quickly to you. So I just wanted to give you guys some introductions to operational amplifiers, and from here you should be able to go through and start working some problems and being able to really become efficient within the analysis of basically op-amp style circuits. So more to come on that. So see you next time.